Understanding Interest Rates, Chapter 5, Part 2. Following up the learning outcomes from this part. Now, so far what we've done is we've seen the time value of money equation, or the TVM equation, for 4 of the factors: present value, future value, rate, and time. In this particular presentation, we'll be seeing how to compute the present and future values of multiple cash flows. We'll look at how to compute the present and future values of annuity and annuity due. So these multiple cash flows can be constant or not constant. Let's see how. So to see that, let's assume that this is time t equals 0 and then equals 1, 2, 3, and 4. And these payments, the intermediate payments, are, let's say, so they don't start right now. They start after 1 year. 250, 375, 425, and 575. These are not constant cash flows, but they're intermediate cash flows. If they are constant like this, 250, 250, then this is called annuity. This particular annuity is a 4-period annuity. And then we can do things with it using the time value of equation. Does not mean that we cannot do things with a cash flow stream that has variable cash flows. We can do things with that too, but it's just a little bit more tedious. So let's go back to creating this annuity. All right. So then we compute the present value of perpetuity in this particular presentation, and later on we'll talk about different loan types with comparing them by the nature of their repayments. And then we'll talk about annual percentage rate, equivalent annual rate. What if the rate of interest was not compounded per the number of periods that we have? So for example, if it's annual compounding and we have 4 years, but it could be semi-annual compound, that is compounded per half year instead of per year. So we'll talk about that later on, not this presentation. All right. Now here we're going to try and find out the future value of annuity. Constant payments, but what is the equivalent value at the end of a certain point of time? Now the example of this is, classic example is our retirement funds. We keep on investing money in our retirement funds and we expect it to attain a certain value by the end of some number of years. And that's the intuition. So to simplify it, let's assume we make 4 equally spaced payments of $250 and the rate is 10%. To look at it on a number line, it's pretty straightforward. T equals 0, T equals 1, invest 250. T equals 2, invest 250. T equals 3, invest 250. T equals 4, invest 250. The future value of $250 invested at the end of 4th year at that point of time, same point of time, is the same thing, $250. But that which was invested at 3rd year will actually get time to accumulate interest for 1 year. That's the difference between 3 and 4. So it's going to be 250 times 1.1. Remember, this is 1 plus rate, right, to the power of t. And what is t? It runs for 1 year, so that's t. So the 1 year is a difference of 4 and 3, which is 275. Now, the amount, the value invested at the end of 2 years has 2 years to run, and therefore it's 250 times 1.1 to the power of 2, or 302.5. The best situation is the money that we invested early. $250 invested at t equals 1 gets 3 years to run, 1, 2, and 3. So it's 250 times 1.1 to the power 3, or 332.75. Now, each of them have a contribution to the final value, or the future value. And so we have to give some weight to each of them. The sooner it was invested, the more valuable it is. But each of them have a value. So the future value of this annuity is the future value of the 4 cash flows is 1,160.5. Now this is the way we actually can do it here. So here we'll say equals future value, and we have to give a rate here, so 10%. So we'll say equals future value, and this is $1. We fix the cell D1. Number of periods is, now that's the trick part. So it's going to be the difference of $7, B$7. Number 4 is constant, but sometimes it's going to be -1, -2, -3, and so on. Because the room to run keeps shrinking as the time increases. The value invested at that point of time is 250, and the type is 0. This can also be done like this, equals parenthesis 1 plus $1 to the power of parenthesis $7 minus B4 times 250 times C4. So present value times 1 plus rate to the power time. Future value of D1, the number of periods is B7 minus B4. The starting value, we said it's PMT, so that's 0. The starting value is C4 and the type is 0. Okay, so same answer obtained from both the methods, and then add it together to get the future value of the annuity as 1160.25. Now all this can be done simply by using the TVM equation, equals future value, D1 rate, 4 periods, payment is minus 250, and the present value didn't start with anything, and the type is 0. Magically, same answer. So why did we illustrate these two methods? We illustrated these two methods because this can be extended to use variable cash flows, but this wouldn't work if we had variable cash flows. So for now, we're just concerned with annuity, and therefore we got the 1160.5. So both these methods are illustrated here, and the best way to find out the illustration actually is just right click on this object, worksheet object, open. When you open it, you will see all the calculations being laid out. Okay, close that, and let's go back to work. So now to summarize, the key points are, this is called a 4-period annuity. It starts today. It starts at t equals 0, but there is no cash flow available. So we just signed the contract right now, saying that we'll pay you after 1 period, 2 periods, 3 periods, and 4 periods, kind of like a loan, a car loan or a mortgage. We sign the line, dotted line today, and then start paying afterwards. Same thing. But bottom line is we bring all of the cash flows to the same point of time. In this case, we've compounded it to find out the future value. We could even discount it to find out the present value, which I'll show in just a minute. So then we add the equivalent values of each cash flow to obtain a single equivalent future value or a present value of the annuity. Now this is easily extended to multiple unequal cash flows, as I just showed in the previous minute. Now let's connect the present and the future values using this. First of all, remember it was a 4-period annuity like this. Instead of going to the future, we're going to bring it back to today. So what is the value of 250 invested after year 1 today? So that 250 is not really 250 today. It has to be somewhat less than that. And to find that, we use the discount factor, 1 divided by 1 plus rate to the power of t. That is the discount factor. Multiply 250 by the discount factor to get the present value. Similarly, that will be to the power 2 here, to the power 3, and to the power 4. Add these together to get a single present value. Oh, wait a minute, this was just for illustration. To do it simply in Excel is really powerful. Equals PV, the rate is D1, the number of periods is 4, the payments, equal payments are minus 250. Again, remember, it does not start today. Annuity starts today, cash flow after 1 year, nothing, no extra payments available at the future, and the type is 0. It's going to give us the same value, 792.47, that we saw here. Now, could we have done this here? Of course we could have. So equals this divided by, let me remove the confusion. So I'll just hide these columns. So equals, but put the 10%, right? equals this divided by parenthesis 1 plus $1 to the power of B4, the number of periods. So we discounted by 1 period, discounted by 2 periods, 3 periods, 4 periods, add them up, answer is the same. Well, as if this was not enough, we could even use the PV function. Present value of $1, number of periods is the corresponding period for that cash flow, right? And the payment that we receive in between that is 0. But this value is available to us at the future, and the type is 0. So Control D, Control D, Control D, Control R, same answer. Magically, we could also find out the equivalent of this divided by 1 plus $1. Now, what was 1160.25? It was the future value of the annuity. To find out the present value, just discounted by 4 periods, 792.47. So you can see there are multiple ways to find out the present value of annuity. Some of them are given here in the PowerPoint. And the simplest one is just use the PV function. Again, the caveat is that payments are constant in between. For variable payments or cash flows, not going to work. So for your reference, this is available in a table. And the contrast now, we'll go to the first application of annuity or extension of annuity, annuity due. Annuity due's cash flow does not start at t equals 1. It starts right away. The annuity due starts right away. The payment also starts right away. Kind of like a lease payment for an aircraft or a lease payment for a rental apartment, etc. We sign the dotted line, make the payment, and start living. Sign the dotted line, make the payment, and take the aircraft away or take the vehicle away for if it's a leased automobile. So the annuity due and cash flow both starts at the same time, t equals 0. Since it is available, the cash flow is available right away, annuity due is more valuable than annuity by a factor of 1 plus r. Now let's look at our example again. So instead of being available after 1 period, the cash flows are available right away. So let's do that in here. So I'm just going to remove this really quick so that we don't clutter our heads. So T and the payments. Remember, it's annuity due, so equals 0, 1, 2, beginning of first year, beginning of second year, beginning of third year. That's it. And beginning of fourth year. So first year, second year, third year, fourth year. The payments are each 250. So 250, 250, 250. What do we find out? Present value or future value? For simplicity, let's do the present value. Meaning the present value of each cash flow. So equals this divided by, I didn't put the rate, let's put it here, 1 plus rate, and fix that, $13, right? Fix that to the power of, well, it's available right away. So nothing, it's power of 0, 10%. And then Control D, Control D, Control D. And the present value will be sum total of all these. So you want to see the connection of this. How is it more valuable than the present value of annuity, which has cash flows further out? Well, just divide this by 1.1, 1 plus rate. And you will see that the present value can now be equivalent to each other. Look at that. The yellow cell is the same as this present value of annuity due divided by 1 plus r. They're the same thing. So annuity due is definitely more valuable than annuity. Bottom line is this: the sooner you make payments, the more you'll get in the end. Okay, moving on. Second application of annuity is perpetuity. Perpetuity has infinite cash flows. And it can be shown that the present value converges. As the cash flows become further and further out, they become meaningless to us today. For example, 1,000th cash flow. What is the present value of 1,000th cash flow? So if t equals 1,000, and the rate is 10%, and the cash flow value is 250, what is the present value? So this is the future value of this cash flow. And the present value will be equal to 250 divided by 1.1 to the power of 1,000. It's basically 0. So what it illustrates is after a sufficient amount of time periods, the additional incremental cash flows are meaningless, even though it's a perpetuity. Perpetuity means forever, right? So the present value is essentially C over R. Now remember, this present value is for infinite cash flows, okay? And C is the cash flow, R is a discount rate. Very quickly, I can give a quick illustration right here, or maybe a small illustration right here. So it's T equals 0, equals this, plus 1, and then go to, let's say, 550, A 550, and then paste it. So we have, equals B2, A2 plus 1, A1 plus 1, sorry about that. So we have 550 periods, and let's assume all of them give us $250 as equal payment. Now what is the present value? Well, not at T equals 0, right? It's annuity. Oh, right. Equals, now let's put a rate here. So rate is 10%. Equals this divided by parenthesis 1 plus $1 to the power of A2. That's the present value of that cash flow. As you can see, as we go down, these cash flows are meaningless. So the sum total of all of these is going to be C over R, or the equal cash flow of 250 divided by 10%, or 250 divided by 0.1, or 5,000. Sorry, 2,500. So 250 divided by 0.1 is 2,500. So why did we have to do this exercise of calculating the present value of each cash flow? Well, you could have just used the C over R formula, right? That's what we did here. Moving on. Now let's talk about a mini case. In this case, Grace F just graduated from college and she's very thoughtful. She's going to say, I learned compound interest and the power of compounding from my corporate finance class. I'm going to use it. So she says, I'm going to create a nest egg or retirement funds. So she's going to invest $12,000 per year for 45 years until she retires. Now, her objective is to get the best possible rate. So she approaches advisor Matt B and asks for a suggestion. Matt B, the expert that he is, given his experience in stock markets, says 11% in just a simple overall stock market. So what happens now is Grace F just invest $12,000, 45 years, 11%. And so let's just create a new sheet here and see what she does. So it's an annuity, right? Starts at the end of the first year. So payment is $12,000. Rate is 11%. Time, or NPER, is 45 years. And she needs the future value. So equals FV, rate, number of periods, the equal payment, again, loan consideration, so minus the value today, didn't start with anything, and type is 0. So she ends up with $11.83 million at the end of 45 years. So both the ways are given here in the PowerPoint that's associated. Feel free to play with it using that same thing, worksheet object, open, etc. Now, the case continues. Grace F now has accumulated her wealth. She wants to disinvest it and enjoy the money. So she approaches Matt B again, who tells her, well, 11% is still the going rate. Now, how do you disinvest this cash flows through constant payment right away so that she's going to be left with nothing in 25 years? To do that, to find that number, now remember, this is annuity due because she's going to withdraw immediately. So she wants to find out that constant payment at the end of 25 years, which will completely finish this money. So equals PMT, we use the PMT function, the rate still 11%, the number of periods is 25, the present value, the value right now is this, the future value, want to finish it completely, so 0, and the type is important. It's not the end of the period anymore because we want the money right away. So it's the beginning of the period. And so these constant payments now are 1.26, so she can withdraw $1.3 million potentially every year for next 25 years. And so that's what we do here. The calculations are showed in this table here in detail. Again, worksheet object, open and enjoy. or we can use the PMT function. Both give the same answer. All right, to conclude, annuity has equal cash flows available at the end of the period. Annuity due has equal cash flows starting right away. We must bring all the cash flows to the same point of time to compare them. Present value of an annuity is the value of cash flows, this equivalent value today. Future value is this same equivalent value in the future, but at the same point of time in future, not at different points of time. Annuities and annuity dues have many applications, one of which we saw in this presentation. Next, we'll talk about different loan types, APR, equivalent annual rate, periodic compounding, etc. That is chapter 5, part 2. Thank you for listening.